now I like to briefly introduce the speaker of today, Florian Buyse. He's a geoscientist specializing in advanced X-ray imaging techniques for the three-dimensional characterization of geological materials. He's a postdoctoral researcher at Ghent University's Department of Geology and works closely with the Ghent University Center for X-ray Tomography. And his research focuses on high-resolution X-ray microcomputed tomography and spectral imaging methods to study the internal structure and mineral composition of rocks. And in particular, he works on micro-CT techniques that introduce chemical sensitivity into laboratory imaging, enabling improved mineral identification in 3 dimensions without destroying the sample. Today, Florian will present recent advances in both standard and spectral micro-CT and show how these can enhance non-destructive mineral discrimination in complex geological materials. So please, Florian, take it away.
Thank you for the introduction. I will start sharing the presentation again. Now the presentation should be visible. Yes? Okay.
Yes, sorry, yes.
Yes, so again, thank you for the introduction. As said, I'm investigating actually what is possible with X-ray CT in terms of chemical sensitivity, with the main goal to identify minerals in CT scans. So the work that I will present is work that I conducted during my PhD, and I will show what I'm doing right now during my postdoctoral research, building on my PhD work. So the main problem with mineral identification via X-ray CT is really that can we segment all the minerals that we can see in an image such as this one and really map their distribution in 3D? So the first question is, which minerals do we see and to what extent can we really differentiate them? Ultimately, the goal is really to automate mineralogical analysis in 3D and combine this with other techniques as a verification process. So for today, I will talk about these subjects presented here. I will start with the principle of X-ray absorption. This is first theoretical important parts, then talk about sample composition, the quantitative assessment from knowing the minerals to knowing the system, then implementation of spectral CT, and some of the current work I'm working on is combining X-ray CT with neutron CT for their complementarity and chemical sensitivity. So we'll start with a short introduction of the principle of X-ray absorption. This all has to do with the Beer-Lambert law, which, as you can see, the mathematical description of this law here. What we actually measure while doing CT scans is the intensity. I'll maybe change my pointer to a laser pointer. So what we measure is the intensity at the detector, starting with the initial intensity from the X-ray source and everything that influences this initial intensity. So what we're looking at actually in the image is the attenuation coefficient, which is dependent of the density of the material, but also the chemical composition. And between brackets, you can see the chemical composition. What we see here is actually the effective atomic number, so the average of the material we're investigating. If we're looking at all the elements, we can say that with the larger the atomic number is, the more it will influence attenuation coefficients. So for instance, a hydrogen almost does not contribute to any of this attenuation coefficients, while for instance lead is really has a high impact on this attenuation coefficient. So if we look back at the initial image, we can say that minerals that have a low attenuation value, so lower grayscale or darker grayscale values, have often a lower density and are have a chemical composition that mostly, in this case, is like silicate minerals containing oxygen, aluminium, or silicon. So the question is, how can we really define those is by defining the density and the chemical composition of the minerals or of the materials. So that's why we need the second step, as in knowing the sample composition, knowing the minerals, what can we expect while scanning these samples. We can know the minerals in the first step from literature on the geological materials working on. Besides that, we can also do some bulk composition, XRD, XRF, combine this with optical microscopy or SEM-EDS to have an initial idea what to expect and really to know the density and the chemical composition of each mineral within the rock. So useful links to define those is, for instance, Handbook of Mineralogy. You see here an example where you can see the chemical composition and the calculated density that can be used to know the mineral and to actually know the attenuation coefficient better. Another website that is useful is mindat.org, which delivers the same type of information. In my case, I use mostly SEM-EDS since we can not only know the composition, but also actually map them to later link them directly with the CT scans. So this is a combination of imaging, backscattered images, together with spectra taken over these images to create these mineral maps and directly have some input for the identification with CT as well. Actually, we have already everything, but it's unfortunately not that simple, since the principle of X-ray absorption, if we have the incident X-ray photons, there are different interactions with the materials. There is photoelectron absorption and Compton scattering. That is the most important part in the energies we're working on, mostly for visualizing rocks. And besides this, I highlighted here in green, which will be of importance later. It also creates these characteristic X-rays due to the transition from the L to the K transition within the elements. To give you an idea why this is important, if you look at the atomic number of the materials, so let's say of the common rocks, depending of which principle is mostly dominant, it has a different influence on the attenuation. So if we go to higher energies, so mostly let's say we work about around 0.1 mega electron volt, which is 100 kilo electron volts, you have both a combination of both. If you go to higher energies, attenuation is similar to the effective atomic number, while at lower energies, the photoelectric absorption is more dominant and is similar to the effective atomic number, but to a power of 4 to 5. So here you can see that depending on the energy and depending on the material, there is a difference in influencing the attenuation coefficient. So we can plot actually those attenuation coefficients in terms of energy as well. So for main minerals, as in the most rock-forming minerals, you see that these are quite similar to each other. While for more dense minerals, there are these interesting K edges that will be useful for spectroscopy, since this is sensitive, energy sensitive, to really look at these K edges and how these influence attenuation coefficients. So the question I often get, okay, so do you think I can differentiate phase X from phase Y in 3D using micro-CT? Well, the answer is, do you know the system you're working with? Since it depends really on the instrument, as in what is the spectrum of the source, what is the energy sensitivity of the detector, and also your sample itself, as said, the mineralogical composition, which is something we know, but also the shape and mostly the thickness of your sample influences how much of your initial intensity gets through your sample and influences your attenuation. Two papers I want to refer to that take this into account is, for instance, one that was recently published about useful user interface for new users to plan your X-ray computed tomography experiments. This includes your sample properties and your scanning properties. And another one from 2015 is a projection simulator for laboratory-based X-ray microscopy, which actually mimics all these things to check for yourself what is possible with your setup, with your sample. So this last one, you can see here a screenshot from. This is a setup optimizer within this program where you can change the tube, the voltage of the tube, which filter you're using, which detector you're using, exposure time, etc., and check actually for your sample what the reconstructed attenuation would be. So you can do this for one material, but you can do this for every material you're interested in to check either what are the exact system conditions that are perfect to differentiate your minerals of interest, but also to see if you have a multitude of of minerals, is it possible to identify those? So this is what I did as well. So changing from this larger data sets, going through your specific data sets, specific setup, where you can really see, okay, where is my attenuation plotted? Can I see this then in my image as well? So I can answer now, let's find out, by giving you some examples of my work. So here you can see again on the left side some EDS mineral maps, and on the right side the corresponding microcity slice. So I calculated based on this information what can be seen here. And as you can see, apatite and shoal minerals are more dense. So these can be linked indeed with those and are confirmed with what we see from the EDS maps. And also that quartz and albite, for instance, is really close to each other, and that the grayscale values are, in this case, as well close to each other. So by using EDS, you can train and verify this data to even improve the segmentation, for instance. But in most cases, you can already use this relative position of attenuation coefficients to identify the minerals in microcity data. This is an example of this, one sample that I scanned. So by doing this and the segmentation, you can really correlate all the different phases within and orientation in 3D, which is super useful to say something about, in my case, how these minerals were formed. Another example, so this is another map. You can see again, quartz has some lower densities, muscovite a bit higher, apatite highest. And there is one phase that was first identified as being biotite using SEM-EDS. But what you see here is that the attenuation or the grayscale value is somewhere below apatite and muscovite. So this is not correct. The case here was, since I cannot measure lithium directly with SEM-EDS, due to this one little element, you can see that actually the attenuation coefficient can already lower quite a bit. This was later verified, and indeed, I found out that this mineral, which was first thought to be biotite, contains some lithium, and really this reflects as well in your attenuation data. And this is something I'm working on right now as well, to look into the distribution of lithium within minerals, mostly into pegmatite rocks, since this was an interesting found during my PhD. Going back to the previous example, there are some limits, of course, when you have similar grayscale values, in this case, apatite and shoal minerals, although different density and a different chemical composition, you see that the grayscale values can be almost the same. So there are some limits to this. Therefore, part of the work I did was looking at the usefulness of using spectral microcity. as this looks really at these K edges within your energy spectrum or your energy attenuation curve to really directly identify the chemical elements that causes these peaks in these curves. So to test this, I looked into
Still in the copper room with Anik, maybe looking.
Yeah, I will continue. I was looking into high density minerals. For instance, these two, just to give you an example, have also different density, different mineral composition. But by replacing the standard detector with a spectral detector, you can really resolve these energies. Since it's energy sensitive, you can resolve these K edges for each element. So for instance, the KH of 10 is somewhere around 29.2, and for tantalum is around 67 keV. So this is what I looked into. Therefore, I went to DMEC Center for X-ray Imaging, UPA in France, where they have a TESCAN spectral detector. So I tested this with natural samples. You can see here maybe a bit of a difference in grayscale values, but this really comes clear when looking at the spectral microscopy. You see at the attenuation curves that there are indeed peaks at the predicted locations. And also if I switch between those two images, you can see that depending at which energy you really look at, that the grayscale values change. Another example is to test this really with prior knowledge from SEM EDS. So I looked into minerals that contain both gold, silver, and lead. And again, you can see that you can differentiate gold from lead, but also the presence of silver, which is really at the lower limit of what is possible with this technique, can be seen with this technique and is found to be useful to directly identify not only your minerals, but also your elemental or chemical composition. There are line detectors, such as in the system of TESCAN, but there's also normal square detectors. What I did here is use a hexitech detector, which we have at UGT, at our facility at Ghent, where we can really take radiographs and not only a line scan. And here I was interested into looking at the distribution directly of lead minerals and the element lead. So what I did here is to look at KH imaging, look at energies just below your KH and look at energies just above. Subtract them from each other to really recreate the distribution of the element maps, and in this case, the distribution of galena. You can see this in the radiographs, but also below, you can really see that it pops up in your tomographic images as well. So spectral CT, yes, there is a possibility of direct identification of chemical elements. Now you can ask if this is only possible to differentiate those high density minerals, just as such as gold or lead. Well, there is more. Actually, they are developing techniques at TESCAN to really look also at these low atomic numbers. And a test I did with the system again is by looking at those two minerals. So you can see here the mineral composition of orthoclase, and the difference with spodumene is really the presence of potassium compared to lithium, and a big difference in density as well. By looking only at the standard microscopy slides, there is not really a difference here that we can see. But by using spectral microscopy, you can see that for this yellow curve, that it pops up higher at a lower energy. There is some overlap here with the blue one, and the blue ultimately stays below, while the yellow one stays a bit higher. And what they do with this, or what they are developing at TESCAN, is really to use these spectral data combined with deep learning on the images to differentiate directly density from effective atomic number, by which we can say directly, okay, this is K feldspar for only the top part of your sample, and these other things are indeed the spodumene minerals. So this is what I'm using right now to identify lithium-bearing minerals within pegmatitic rocks. Another thing, of course, we can only use X-ray CT, but it's often of interest to complement it with other techniques. And what I'm using right now is a combination with neutron CT at the facility of TU Delft, which is also a lab-based neutron CT lab where they do these type of analysis. And to compare, what we can see with neutron compared to X-rays is that actually the attenuation coefficient using neutrons does not directly depend on atomic number, but is more diverse. So in this case, it was of interest since this has the presence of lithium has a high influence on the image. This is I wanted to test out as well together with TU Delft. And here you can see such a comparison. It's the same image as before that I tested with spectral CT, but now you can really see that where we had these lithium-bearing minerals compared to the K feldspar minerals next to this. From X-ray CT images, you cannot directly see those, while with neutron, you can see that the minerals containing this lithium are really popping up. The same for these micas laying around here. If we go back, lithium and both hydrogen have a high influence on your attenuation coefficient using neutron. We can plot this again now combined for X-rays on the x-axis and neutron on the y-axis to look really if it has a higher density. We can see those with X-rays. If it has a high influence of hydrogen or lithium, it has more sensitivity to neutrons. And for instance, for boron-bearing minerals, it has really high influence for neutrons. To really then again define those minerals in 3D. And if you look, this is the last slide, if you look to the joint intensity distribution of both neutron intensity and X-ray intensity, you can see really these clouds that can then be linked again or can be used to actually identify minerals within your rock samples. Just as a summary, I started with explaining the principle of X-ray absorption, which is not that simple, although we know the minerals and know the system. But combined, we can actually use those to identify minerals already. A new thing that is of interest is using spectral CT, as this allows to directly identify chemical elements. For sure, for high atomic numbers and even for low atomic numbers, it's of interest to use this technique. There is an example of such an application already published by the DMEC Center in Pole, where they differentiate, for instance, calcite from dolomite using this technique. And now I'm working on the combination of neutron CT. There's more to follow, but just to give you an idea already, there is possibilities when combining those with X-ray CT to have an extra complementary chemical sensitivity. So yeah, this was my presentations. Thank you.
Fantastic, Florian. Thank you very much for your very clear talk. So please, if you have any questions, raise your hand and I can give you the floor. Or put your question into the Q&A or the chat and I can pose the question for you. So feel free. Just gonna browse around. Meanwhile, I have a question. So what are the next developments needed to make spectral micro-CT more widely accessible to geoscientists in both academia and industry? So is it accessible and if not, how can this be achieved?
Well, when I started my PhD, it was in 2019. This was not yet commercially available. For all I know of, the one commercial system that is available is the one from Tescom. As these developments go, I think in the future this will be more and more of interest and will also increase in terms of accessibility. But just to say, it is one of the extra things that can be used, but don't limit yourself. If you only have X-ray CT, the standard one, there's already a lot that you can do from this one. If you know your materials and your system well, I think it's already a good start for looking into identifying all these minerals.
Great, yes. So what kind of segmentation or machine learning approaches are being used to classify minerals in spectral CT data? Do you have an idea?
Yeah, so the most useful one is, maybe I go back, it is the example of the neutron CT, but this can be similar for the spectral CT. You can plot different ranges, let's say for low energies on the y-axis and high energies on the x-axis. And you will see more of a line from your 0 point to the high points. And you will see different trends as well to identify those small differences for the minerals. So not only for these K edges, but it's a bit similar to those. You will see some point clouds for each mineral that can be differentiated using the spectral CT technique.
Aha, okay. So I have one question from it's in the Q&A. Have you considered using spectral or EDS maps as training input for AI segmentation of conventional CT data? Do you see possibilities or limitations? It's a bit similar or related at least with machine learning, yeah.
Yeah, the thing there is, I tried this already. The thing is, if you prepare your sample for EDS, means you need to polish your sample, which is in a way not a problem if it's perfectly polished, since you can really recreate the same slice as you have with your CT data. The only problem there is with polishing, it's not always even how you polish. So to have a really, sometimes these edges can be really not well polished, for instance, and there you have then maybe a small difference in mineral composition. Of course, if you only select a zone, and those images are registered well, it is possible to use this. I tried this as well. Of course, you end up with the same limitations, mostly with your X-ray CT data, in terms of how big the differences are in grayscale values. The one thing I often use, if you're worried about, can I segment this? If you cannot see it visually yourself, it's probably not possible to segment those different phases. But if you can see those, you can be quite confident that it's possible to segment those minerals.
Okay, that sounds promising. So I've got a question here from Bastien Walter. I will, please go right ahead.
Yes, hello. Thank you very much for the presentation. I've been reading yesterday your paper from 2025 about spectral XCT.
Yeah.
And I have a question, a technical question, because in your presentation and in the paper, you are showing attenuation profiles.
Yes.
But I was wondering, I don't know which software did you use, but so you're able to select one voxel, one specific voxel, and for each voxel you can plot an attenuation profile. Is that right?
Yeah. That's correct.
Okay, so you have your 3D image, and then you can select one voxel, and you.
Yes.
Or so for looking for coordinates or.
In a way, you can do this, like you said, you can select a voxel. What I did in this work is really select a zone which I know what the mineral composition was to check if it was if it is similar. So you can what it is actually those spectral CT data sets are like again a stack of images, not changing in terms of height, but changing in energy. So for instance, by using Python scripts, you can actually select zones within or to look at the diversity of the different minerals. Since this is like a stack of energies, it offers a possibility to use some machine learning on that stack to directly see where are the differences really, and to automate the identification process of minerals, even without knowing what the minerals would be.
Okay.
If that answers your question, I'm not sure.
Yeah. Thank you. And I just have another one. Because in this paper, you always have a prior knowledge about the samples you're analyzing. Would it be, or is there any advantage to use spectral XCT if you don't have any information about your samples, any other information about the sample?
Yeah, for sure. I did this just to be sure if the system works like it should work. But let's say if you skip this prior knowledge, you would still see the difference between those edges. So you know that there is a different phase. Of course, you don't know what the name is of this mineral phase, but you at least know that there are this number of different phases present using this technique. Whereas if you would only look at, in some cases, only at the standard CT scan of the same slice, the difference is too low, especially if I go back to this example of this deep learning. So this image you see in the center is slicing through these different types of energies. And at first, you don't really see such a big difference between those. But for instance, by using deep learning, or this can be done by yourself as well, I guess, there is a possibility to directly see those minerals here. Of course, I have not recreated this section into a thin section. I just knew that these minerals are present in general in that rock, not specifically on this slice.
Okay. And just one last question. The Python scripts you were mentioning, are they available somewhere, or?
I did not publish them anywhere, no. But
Okay.
if you want some help on this or are interested in this, feel free. I can share or give you some insights on what I used for this.
Sure. Thank you.
Thank you very much, Bastien, for your questions. So I got one more question for you, Florian, if you still have time. I see we're all a bit over, but there are a lot of questions, so I think that's great.
Okay.
So how far are we from true automated analyses? I'd guess that from the spectral CT, we should also get some info about the chemical composition of phases. So automated analyses, I think, is the key here. I hope, Fernando.
Yeah, I think it is possible. The only thing where the thing to do this is actually need a lot of computing power. Mostly I do this on my desk PC here. But in a way, it's possible to do this automated, yes. It just takes time to do this, right? It doesn't need me, for instance, anymore, or a geologist. But this automated will give this automated without interference of me, will give the different phases. Eventually, it's just in the end up to you to really incorporate your knowledge on the material itself to see what this differentiation between the minerals are actually identifying. But it's possible, I would say, yes.
Okay, great. And so when are we going to start this, Florian, this automated analysis?
Yeah.
Oh, you mentioned Python already, right? So you kind of half automated maybe already.
If I have a
In that sense.
supercomputer or I have access to a lot of computing power, yes, I can do this.
So Fernando, it's now if you have the right if you have the computing power.
Yeah, you will
so
only have the limits between differentiating depending on the grayscale values.
right, and you would say that it would have a better chance of using this in combination with the neutron CT, right, to get like the whole spectrum.
Yeah.
Well, all the elements
Yeah,
basically that you
or
can pick up.
it's just an example of how complementary information can lead to better identification.
Yeah. Great. Yeah, I like it. Just like multimodal, multidisciplinary. I think that's really nice. A nice example of that. So with that, I would like to close this session. We're a little bit over, but thank you for your enthusiasm today. And thank you, Florian, for this wonderful webinar. And I hope to see you next month again, and have a great day. Thank you.
See you.